Okay, so in this video, we're going to talk about something called an antiderivative. So but let's just look at an example here. Suppose we want to find a function, capital F of x, whose derivative is f of x equals 3x squared. Now we've done derivatives enough that should be a fairly easy thing to do. The question is, what function do you take the derivative of to get 3x squared? And because we know how to do derivatives, we can see that, okay, well, x cubed would be a function that if you took the derivative of it, you'd get 3x squared. This is what we call a particular antiderivative. It's a function that when we take the derivative of it, we get 3x squared. That makes x cubed a particular antiderivative of 3x squared. And the reason we use the word particular here is because there's actually a lot of different functions that could do this. For example, we could write down maybe f of x equals x cubed plus 2. If I take the derivative of this, I also get 3x squared. So this is also a particular antiderivative. F of x equals x cubed minus pi. That would be a particular antiderivative. If I take the derivative of this, I get 3x squared. So those are particular examples of functions that would give me this as a derivative, and so we call those particular antiderivatives. Now, if we want to represent sort of in general all of these functions, they all have a certain format to them. It's a certain part here, and then if I add on some constant over here, and it doesn't really matter what that constant is, because when you take the derivative of that part, that goes away. But they all have that format. It seems like the x cubed part is the important part here, and that's really actually exactly the case. F of x equals x cubed, and if I just add on some plus c here, and c in this case represents any constant, then what I could do is I call this the general antiderivative. So in other words, the general antiderivative is this general form right here. It's got sort of the important part, and it's got plus c, where c is just some constant. A particular antiderivative is if I figure out what that c is, what that number, what that constant is right there. And usually I'm given some extra information of some type that allows me to find that. So, okay, great. We know what a particular antiderivative is. We know what a general antiderivative is. And we see that, with easy functions, it's not too hard to find these things. So let's get some terminology down and just sort of make sure we understand what's going on here. If capital F prime of x is equal to little f of x, then that makes capital F of x the antiderivative of little f of x. In other words, the antiderivative is the function you would take the derivative of to get little f of x. An antiderivative is also called an indefinite integral. Now, don't worry too much yet about what that means. What is this integral word? What is all of this? Well, okay, we'll get there, but don't worry too much about it just yet. We might want to go over here and kind of look at this as a little chart. Suppose I start off with some function g of x. Okay, so I'm given some function g of x, x cubed, sine of x, whatever that function turns out to be. If I take the derivative of that, then I've found g prime of x. But suppose that I'm starting over here. Suppose I'm starting off with g prime of x, which I'm going to call little f of x. All right, so little f of x is the derivative of some function back here. Then the antiderivative takes us from little f of x back over here to find the function that I took the derivative of to begin with. Okay, and we call that capital F of x. Suppose that I start off with, x cubed. All right, so I take the derivative of it and I get g prime, which would be 3x squared. So 3x squared is my f of x. But when I take the antiderivative of that, well, okay, I get the x cubed, right, the thing I start off with, but this could be x cubed plus 1, or x cubed minus 3, or x cubed plus pi, or whatever. So these are not exactly equal, but they belong to the same family of functions. Okay, so I know that we've done this one just a minute ago, but let's just make sure that we understand. So find all antiderivatives of f of x equals 3x squared. Well, all antiderivatives means we're looking for the general one. So the general antiderivative would be x cubed plus c. Now let's talk about the indefinite integral notation. And again, I don't want you to worry a whole lot here about what do these terms mean. We'll get there, but we're just not quite there yet. Right now, let's just think of this as being a notation. So we've got this elongated s right here, which actually stands for the sum of something. We've got this dx over here, which is called a differential. And essentially, this right here is going to tell us what is the important variable that we're dealing with. dx. X is the variable that we're dealing with. So we got some function here involving x, and we're going to do something here with respect to x. Now, the reason that you kind of have to indicate this is because it is possible, and you'll see this if you go on into your next calculus sequence. It is possible that you end up with functions that have more than one variable. You may have functions that have x's and y's and z's and w's and all kinds of things. And you're going to do this integral notation to it. You're going to do some kind of operation here. Well, you need to indicate which variable is the important one. And so right now, this is just part of the notation here. And what this means, what this notation means, we're going to see kind of where this notation comes from, in a different video. But right now, what this means is you're looking for the general antiderivative of this function. All right, so that's what we're doing. We're trying to find the general antiderivative. We're trying to find the indefinite integral, which is just the same as the general antiderivative. So here we go again, our favorite function. We want to evaluate the indefinite integral of 3x squared with respect to x. And we know that the indefinite integral, all we're really doing here is just sort of making sure we're getting comfortable with the notation. The indefinite integral with respect to x of 3x squared is going to be x cubed plus c. All right? And that's how we write those types of things down. Now, sometimes you'll hear me kind of slip up. Sometimes I won't say the indefinite integral. Sometimes you'll just hear me say the integral of. But if you see just an elongated s here and there aren't any numbers or anything kind of hanging around it, then this is an indefinite integral. It just means you're dealing with the general antiderivative. All right, so let's see if we can do some of these things. I want to evaluate the indefinite integral of 7 with respect to t. So what this tells me, now watch out, I know that my variable that I'm dealing with here is t. So the function I'm talking about involves t as its variable. The function I have is just a constant, it's just 7. So what would you take the derivative of that would just give you 7? Well, the answer is you would take the derivative of 7t, right? So the derivative of 7t, and I know it's a t because this differential over here told me that t was my important variable. I need to add on my plus c here to represent all positive derivatives. But if I came along and took the derivative here with respect to t, I would just get a 7. The c would go away because it's a constant. I'd end up with my function in here. And I think that this shows you that there's an automatic check that's kind of built into these problems, right? If I take the indefinite integral of 3x squared dx, I get my answer. If I want to check the answer, all I've got to do over here is take the derivative and see if that gives me this thing here in the middle. All right, so we've seen a couple of examples. So let's talk about some integration rules. Integration rules. Integration is just the word we use here. It's the process of finding integrals. All right, so let's talk about some rules. We have the power rule, which says that if I am trying to find the indefinite integral of x raised to the nth power, then what I'm going to do is I'm going to add 1 to that exponent, and I'm going to divide by the same thing. And if you think about it, we know that we're doing the inverse operation of differentiation here. All right, we're trying to undo derivatives. And so what we should be doing is sort of the inverse operations that's involved in all these different rules that we've seen with derivatives. Remember, if you have x to the nth power and you're doing the derivative, that n comes out in front, and then you subtract the exponent by 1. And so if we're going in the opposite direction, it's not surprising to see that we add the exponent by 1 and then divide by that same number. And that's what we get right here. And you can see, hey, if I wanted to check and make sure this rule was right, I would take the derivative. If I took the derivative with respect to x, I would get an n plus 1 out in front, which would cancel with the 1 in the denominator. I would subtract the exponent by 1, which would just give me x to the n, and we got it. So this is the power rule. The linearity rule is pretty much the same one it is as when we saw the one with derivatives. It says that if you've got some constants being multiplied by functions, well, just leave the constants alone. They're not hurting anything. You're just going to kind of carry them along, and do the important part here with the functions. So a times f of x plus b times g of x. If we're trying to find the antiderivative of that, then we're just going to leave the a where it is and find the antiderivative of f of x. I'm going to leave the b where it is and find the antiderivative of g of x. The constant rule, if I've got a constant here, then when I take the antiderivative of that, or the indefinite integral of that, I'm just going to multiply that by whatever the important variable is there. The trig rules, we've got a couple of trig rules here, 3 of them in particular that we're going to think about. One is the antiderivative of cosine of x. So you say, hey, okay, well, what is it that I take the derivative of that gives me cosine? And we know that turns out to be sine. Don't forget to add your plus c to make it a general antiderivative. What is the derivative of sine? Well, we know that is cosine. But if you were doing this the other way around, the antiderivative of sine is negative cosine. And that's because if you took the derivative of cosine, you would get negative sine. And so you get an extra negative kind of popping up in there. So this is going to be negative cosine. And then when you take the derivative, you'd get negative sine, which would take you back to here. And that's what you get for the antiderivative of sine. Well, this one's here. This is one just that we just throw in here. If you went back and remember, in one of the earlier videos, I did the derivative of tangent. It turned out to be secant squared. So the antiderivative of secant squared is where you get your tangent. All right, so let's look at some examples. I want to evaluate the indefinite integral of x cubed plus 5 with respect to x. All right, so that is going to be, let's see, the power rule tells me x to the nth power, add 1 to the exponent, get the same number downstairs. So it looks like I get an x to the 4th over 4. If I've got a constant there, I'm just going to multiply that constant by whatever the important variable is. So I'm going to get a 5x. Don't forget to add on your plus c. Now we may make that look a little better. There's different ways of writing this, but it's an equivalent answer. And there we go. Well, what about this one? Well, it looks kind of complicated, but honestly, not too much. We're evaluating this indefinite integral. We're trying to find the antiderivative with respect to t. All right. So I'm going to take it one at a time. Let me see. I've got, this is going to be equal to, I'm going to leave the 5 where it is. The t to the 4th. Okay, so I'm going to add 1 to the exponent, and I get that same number downstairs. Okay, I'm going to leave the 10 where it is. T to the 3rd. I'm going to add 1 to the exponent, and I get that same number downstairs. Minus 3. I got a t to the 1st right here. So I'm going to add 1 to the exponent, get the same number downstairs. And I got a 2 right here, so I'm going to multiply that 2 by the constant. I got t's in this case, so that's going to be 2t. Do your plus c there. And now it's just a matter of cleaning things up a little bit. Hey, those 5's cancel out, giving me t to the 5th. I've got 10 over 4, which is 5 halves t to the 4th. I got minus 3 halves t squared plus 2t plus constant. Looks like we're done. All right, I want to evaluate the indefinite integral of the square root of r. Okay, now let's see here, the square root of r. Now, first, let me just make one point real quick. It's easy to get into the habit of just always thinking, hey, our variable is x. Like up here, when we had this 2 all by itself, a very common mistake that I see is that if you get the 2, you just say, oh, okay, well, that's got to be 2x when I do the antiderivative. Pay attention to what your variable is. It's actually 2t in this case, and so just make sure you're paying attention to your variable. So in this run, okay, well, I don't have any kind of rules that tell me about square roots, but we'll use the same strategy we did when we first started learning about derivatives. I'm going to rewrite my problem so that it fits one of the rules. So I'm going to rewrite this as r to the 1/2. Now, be careful here. I haven't done any calculus to this at all yet. I have not done anything here. I haven't done any antiderivatives. I'm not evaluating the indefinite integral yet. All I've done is rewrite this thing. So make sure you carry this notation along when you do that, because I haven't done what this notation tells me to do yet. All I've done is I've just rewritten the function. But now at this point, I'm about to find the antiderivative. So at this point, this notation is going to go away, because I'm going to add 1 to the exponent. That gives me 3/2 up there. And I'm going to divide by the same number, 3/2 on the bottom. Okay, so you see at this point, the notation, the indefinite integral, that big elongated s and the dr, that goes away because I actually did the calculus part right here. I actually found the antiderivative. Everything else here is just a matter of cleaning things up. Let's see, if I multiply the top and bottom of this thing by 2, you see that would cancel the 2 down there, and that would end up giving me 2/3 r to the 3/2 plus c. And if I wanted to write that as the square root of r cubed, then I could do that. But basically, I've got it right here. Okay, so be really careful with that notation. Remember, sometimes we have to rewrite things here, and really pay attention to at the point where this notation goes away. Like we didn't really see that up here in these problems too much, because we just started with the problem and we went right into the antiderivatives. But if you've got to do some kind of algebraic manipulation with your function first, keep that notation there, because you haven't done any calculus yet. It's at this point when you're using those rules that the notation goes away. Okay, let's see. Okay, well, I've already done that one. Looks like I just have a problem that's repeated there. How about we look at this one right here? We want to evaluate the indefinite integral of 4/x² plus 5 times the cube root of x. We want to do that with respect to x. Okay, so looks like, I'm not ready to just jump in and start doing antiderivatives yet. It looks like I got to do a little bit of algebra before I can do that. So remember, we're going to keep this notation because I haven't done any calculus yet. I'm just rewriting this as 4x to the -2. And I'm going to rewrite this as 5x to the 1/3. Okay, so that elongated s and the differential has to stay there because I haven't actually done any of the calculus yet. All I've done is rewritten my function. But now I'm ready to do it. I've got this in the form that I need it in. So I'm going to add 1 to the exponent. So I got a 4 here. Add 1 to -2, I get a -1, and that number also shows up downstairs. I got a 5 here. Let's see. Add 1 to 1/3. I'm going to end up with x to the 4/3. And I get a 4/3 downstairs as well. Don't forget your plus c. And now the rest of this is just rewriting and doing a little bit of algebra. So let's see. I've got a negative. I've got a 4. That x has a -1 to it, so that's really downstairs. So I got a -4/x here. All right, let's see here. If I multiply the top and bottom of this big fraction by 3, you see the 3 down here would cancel that 3 out. So it looks like I would end up with 15x to the 4/3 over 4. And yeah, maybe I could do something else here. Maybe I could rewrite that as the cube root of x to the 4th or something. But really, I've done my antiderivative, and it's in a fairly simplified form. And so I'm pretty much done at this point. Okay, so I'm going to stop this video here. This is a good point to go and just kind of practice some of these things. What we're going to do after this is sort of go in and see where we're going to apply this. But at the moment, we're just, trying to get the skills down. So this is a good point to go and practice some of that.